Just let me know if you have any questions if you've joined us so far. Yes, there's no one here so far.
I have a question. Why are you teaching chemicals?
There's two people, but no, this isn't the right ones. We'll discuss this later. Yeah, so let me know if you have any questions if you joined us. There'll be a quiz on Friday about the heat equation. Yeah, let me know if you need help with the heat equation or anything like that. Oh, yeah, number 5. So number 5, I believe, is the calorimeter problem. Let me take a look. All right, yeah, so with these calorimetry problems, you're just taking two heat equations and setting them equal to each other. Because when it comes to heat transfer, it's the same heat that's going from the hotter object to the cooler object. It's the same heat. So you just set it up like this. So in calorimeter problems, it's the metal that's hotter. So since it's releasing heat, it's exothermic. So that's why I put the negative sign here. The negative sign means it's releasing it, exothermic. The water is absorbing the heat. But I equate them to each other because the magnitude's the same. It's just there's a negative sign here. for direction. So we have the mass of the water times specific heat of the water times final temperature minus initial temperature of the water. All right, so you set them equal to each other. I forgot the negative sign. Sorry, it's kind of crammed there. But yeah, so this is all negative because I know this delta F is going to be negative. So that way the negatives can cancel out anyways. So let's see. Our mass, excuse me. We're looking for the specific heat of the metal. So I'm looking for the C of the metal. So I'm just going to get that by itself first. So I'm going to divide both sides by everything else. All right, so I'm just going to algebraically just get it by itself, divide both sides. So then the specific heat of the metal is the mass of the water times the specific heat of the water times the change in temperature of the water, all divided by the negative mass of the metal times the change in temperature of the metal. Right, so I flipped it left and right just to make it look more like the way we traditionally read. Right, so it's like that. Let me know if you have any questions so far. I'm just getting the specific heat of the metal by itself right now, just the C of the metal by itself. And then I'll plug in the values. All right, so I'll probably do it on the back side though. So they're both 25 grams. That's at least nice. So 25 grams. The specific heat of water is 4.184 joules per grams degrees Celsius. That's big units. And it's going from, for the water, it's going from 20 to 29.4. So I'm going to do 29.4 degrees Celsius minus 20 degrees Celsius. And I'm dividing it all by negative mass of the metal, so 25 grams, times, this one's starting at 75, I believe, and then going to 29.4, yeah. So 29.4 degrees Celsius minus 75 degrees Celsius. Okay, so keep in mind, with all the variables here, the initial temperature of the water is unique to the water itself, right? That was 25 or 20, I think it was 20 degrees. Yeah, 20 degrees Celsius. And the initial temperature of the metal was unique to itself. It was 75 degrees Celsius. But the final temperature is the same for both of them. That's why it's just TF and TF. Sorry if it's kind of hard to read. But the final temperature will be the same for both of them because when you have a hot object releasing heat to a cooler object, it's going to continue doing so until they're at equilibrium. They're the same temperature. So I'm just going to flip this over and show you all the numbers. Right, so it looks like this. So the mass of the metal and the water are the same. So since this is all multiplying, you can probably just cancel the 25s if you'd like. The specific heat of the water is 1.184. And then for the water, it's 29.4 minus 20. But for the metal, it's 29.4 minus 75. So this is going to be negative, but that's fine because that negative will cancel out with that negative, and we'll get a positive value. So let me see here. I think, I can't remember if you got it right or not from what I saw. Some people almost got it right, but then there was like a calculator error, so maybe that was the case. So I just kind of put everything together in parentheses. I don't know if you can, yeah, you probably can't really see that. I don't, I'll try my best. But I just kind of like do double parentheses there. So for 25, and then there's the specific heat of the water. And then 29.4 minus 20 for the water, but I close it with an extra parentheses. There's two parentheses there. So that's just the numerator. And then let me divide it by the denominator. The denominator is negative 25. So, you know, I just divide it, but I do one parentheses in the front just to include the whole denominator together as one factor. And then negative 25, and then times 29.4 minus 75. But again, I do a double parentheses at the end there just so it can all stay in the denominator. So you should get, yeah, 0.86, about 0.86. So the grams cancel. The Celsius is all cancel. So you get 0.86 joules per grams degrees Celsius. So that should be your final answer there. Let me see. Oh yeah. You mean how I put it in the calculator or the whiteboard stuff? So in the calculator, I basically just do this. 25. Yeah, this is like a lifesaver thing. One of my friends taught it to me in high school, and ever since I figured out how to do this, whenever I had a huge long math computation, even with a numerator and denominator like fractions, I just did it all in one step in the calculator. So hopefully this makes sense, and hopefully you can just do this from now on. If you have a scientific calculator like this, or even one of the more complicated ones, some of the cheaper ones you won't be able to do it with this. I mean, you might be able to, but it gets confusing with all the parentheses and stuff. But this is what I do. So 29.4 minus 75. Let me double check. So yeah, you're gonna notice I just put it all in. So I literally just typed in right now. I'm gonna send it to you in a sec. I literally just typed in what I would put in the calculator. It's just all one straightforward typed out computation. But I have double parentheses on the top just to kind of include that whole thing as the numerator, and then divided by that slanted sign, and then double parentheses on the bottom. So it looks like that. So just parentheses, and then a set of parentheses for 25, a set of parentheses for 4.184, a set of parentheses for 29.4 minus 20, but then you need that extra one to close off the whole numerator, and then divide by the parentheses for the denominator, and then you have a set for 25, a set for the change in temperature, but then you have that extra one at the end to close off the whole denominator. So if you just put that in the calculator just like that, and if you have a scientific calculator like this, or a TI-84 or whatever, if you literally just type it in like that, you should get 0.86. Yeah. Yeah, let me know if you guys have any other questions or anything. One second. If you have a question, I'll be right with you. I'm just gonna double check something real quick. Oh. You get 0.86 as well. Oh, okay. Yeah, you're fine then. Yeah, the answer should be 0.86 joules per gram degrees Celsius. So yeah, kind of like that gas constant, the R constant in the last unit. Specific heat capacity just has these crazy units, joules per grams degrees Celsius. Green 2020. Green 2022. Hey, Mohammed. Yeah, those are the units for the heat capacity. It's defined Celsius. So yeah, it's 1 joule per gram degrees Celsius. Truth be told, something like that, a calorimeter problem, I don't even think it's on Friday's quiz. If it is, it's a bonus question, so it'll be more straightforward, like just plain heat equations. But sometimes it gets kind of tricky. I don't think you had this problem, Ryan, but I know some students might. where there might be some tricky cases where you're given everything, but you're looking for one of the temperatures in here. And so some students just get confused by that algebraically. So I think you were fine though on the worksheet. It's divided by MC on both sides, and then you add the final temperature, right? Because some people get confused and they divide everything, including this TF, and that wouldn't work. So, but yeah, it's mostly just the heat equation. Maybe a couple conceptual questions just about yeah, let me know if you guys have any other questions or if you need any help at all. Oh yeah, sure, I can do another one. One moment. Let's see. So I have to see if I can find one. Okay, so let's say we have, I'm not going to write the whole instructions on this just because it'll take too long, but I'm just going to say the mass of the water is 100 grams. The mass of the HCl 75 grams. Specific heat capacity of the water is 4.184. The initial temperature of the HCl is 44.6 degrees Celsius. Yeah, in this whole unit, the temperatures are always going to be Celsius. It's never going to be Fahrenheit or Kelvin or anything like that. The initial temperature of the water is 24.6 degrees Celsius. Okay. And let's find the specific heat capacity. Yeah, for these problems, we're typically just focusing on trying to figure out the specific heat capacity. Hey, Josh. Hopefully you're able to figure out your Canvas information. I don't think you've seen any of the stuff on there yet, so hopefully you can figure out the Canvas stuff. So I didn't write it out like instructions just because it'll take too much room. But we have the mass of the water, the mass of hydrochloric acid. So instead of a metal, I'm putting hydrochloric acid into the water. So yeah, mass of the hydrochloric acid, mass of the water, specific heat capacity of the water, the initial temperature of the acid, the initial temperature of the water, and I'm trying to figure out what the specific heat capacity of the acid is going to be. Right, so I'm looking for the specific heat capacity of the acid. So let me see. And we know they're going to both, oh, there's a final temperature I need too. Forgot to mention the final temperature. Final temperature is 31.3. Might be hard to see. 1 second. Negative mass of the acid, specific heat capacity of the acid, final temperature minus initial temperature of the acid. All right, so it's hydrochloric acid. It's kind of hard to see. That's a 31.3. So it's the heat of the water equaling the negative heat of the acid. We have the heat equation here for the water, the heat equation here for the acid. I'm trying to find the specific heat capacity of the acid, right, the HCl. To save room, I just put H here instead of HCl. So I'm going to try to divide both sides by what I did before, the M and the delta T, to get the specific heat capacity of the acid by itself. All right, so let's see what we get there. All right, so releasing the heat. This is the heat equation for the water, the heat equation for the acid. I'm trying to find the specific heat capacity of the acid, which I'm just calling C of H here. So I'm trying to get C of H by itself. So the way I do that is I divide both sides by the mass of the acid times the change in temperature of the acid. So that's going to be on the denominator of both sides, right? So I basically just get this. Just like the last problem, right? It's just instead of a metal now, it's an acid. So in this case, I want to basically just figure out what the specific heat of the acid is going to be. So let me just plug in my values. The mass of the water was 100 grams. Specific heat of the water is 41.4 joules per grams degrees Celsius. The final temperature was 31.3. The initial temperature of the water was 24.6. the mass of the acid. Let me double check something real quick. Yeah, 75 grams. The change in temperature here is 31.3. The initial temperature of the acid is 44.6. All right, so for this one here, I just did this all up here. Now, keep in mind, I looked this up online, and they didn't give me the mass of the HCl. They gave me the density. So I just put up a different value for the mass. I'm sorry, they gave me the volume. They didn't give me the density. They gave me the volume for the acid, and they didn't give me the mass. So I just put 75 grams for the mass of the acid. So the answer I get here for the specific heat capacity, if you look it up online, it's probably not the actual specific heat capacity of the acid, just because I threw up a random value for the mass here. It should have probably been 83 instead of 75, but I'll just stick with 75 because that's what we started doing. So yeah, the specific heat capacity we get here is probably not actually what the acid is, just because I made up the mass randomly. It should have probably been 83. So I put 75 down instead though. So we'll go ahead and put all this together. You know what? I'll just make it 83. You might as well make it 83 because the density is 1.2. Yeah, the density is 1.2. All right, let me just double check. We have 100 milliliters, so divided by 1.2. Yeah, we'll make the mass of the acid 83.3, just to make it as accurate as possible. All right, so here I'll type everything out. Just gonna know it's probably hard to see. So 100 grams for the water times 4.184 for the specific heat of the water times 31.3 minus 24.6 for the change in temperature of the water. Close off all the numerator divided by the denominator, which is negative 83.3 mass of the HCl times the change in temperature for the HCl, which is 31.3 minus 44.6. All right, so I took back what I said earlier. I just made it more accurate. So the mass of the acid is 83.3. Because in the problem here, they just gave me the volume and expected me to know the density, so I didn't do that. But I looked it up right now, and I just did the math and figured out the mass should be 83.3. So again, on the denominator here, I have the mass of the acid times the change in temperature of the acid. On the numerator, I got the mass of the water, specific heat capacity of the water, and change in temperature of the water. Right? Because I'm trying to find the heat capacity of the acid. So I plugged it in like that. I just I made the comment. It's not showing up for some reason. There it is. Okay. So I just put it all in like that. Let's see what we get. I haven't actually put on my calculator yet. Excuse me. Times 4.184. 31.3 minus 24.6 divided by negative 83.3 times 31.3 minus 44.6. So you should get for the acid 2.53 joules per gram degrees Celsius. So that's the specific heat capacity of the acid. And the way I typed it in on the text box here is how I would have put it in the calculator. You can just put it all in at once like that and press enter and you're good to go. Yeah, let me know if you have any other questions about that. It looks like we were pretty close. The heat capacity of acid might be more like 2.6 or something, but we're pretty close. Yeah, let me know if you guys have any other questions at all. I don't think there actually is a calorimeter problem on the quiz this week. There will be one eventually when we have our unit test, but I think for this week's quiz, it's just the heat equation. If there is a calorimeter problem, it's probably a bonus question. Number 4 for the study guide. You're talking about the study guide with the gases? Let me see if I can find it. Okay. So oxygen and nitrogen go to NO2. All right, so you want to write out the equation first, right? So this is from the previous study guide. So you want to write out the equation first, but we need to balance it, right? It's not balanced yet. So I got to add a 2 here in front of NO2. And now I'm going to have 4 oxygen, so I got to put a 2 in front of that oxygen. So I kind of squeezed it over there. So now it's balanced, right? So we had to do that first. And it says we have liters of oxygen to liters of NO2, right? So let me show you. So we're going from liters of oxygen to liters of NO2, right? So we're starting with oxygen on the oxygen side of the house in liters, and I'm trying to go from liters of oxygen to liters of NO2. So it's this little like upside down U shape, all right? Now, I'll do the whole thing like a normal stoichiometry problem, and then I'll just show you the shortcut. So here, I'll just show you the whole thing. So our given was 42.1 liters of oxygen. And we're going from liters to moles of oxygen, then from moles to moles, and then from moles to liters for NO2. It's just kind of hard to see things on here. All right, so I'm starting with liters of oxygen. So that was my given, liters of oxygen. I'm going from liters to moles. So I'm exiting liters, right? I'm exiting the liters, so that's going to go on the bottom. I'm entering moles, so that goes on top. Right? And then next, I'm exiting moles of oxygen, entering moles of NO2. So it's moles over moles. And then I'm exiting moles of NO2 and going into liters of NO2. Right? So if you just have moles on the top or the bottom, right? If you just have moles on the top or just have moles on the bottom, that's when you just put the number 1 down, right? So 1 there and 1 there. And for liters, I don't know if you still have your mole house, but liters is always 22.4. It's always that number 22.4. Right, so just moles on the top, so it's just 1. Just moles on the bottom, so that's just 1. I have 22.4 because that's liters, 22.4 here because that's liters. And then when you have moles over moles, that's when you use the coefficients. All right, so the bottom one is, here, 1 second, just kind of 1 second. It's so hot. Oh my God. All right, so sorry about that. We're trying to go from, in this fraction here, we're going from moles of oxygen to moles of NO2. So I'm exiting moles of oxygen, right? So since I'm exiting moles of oxygen, that's going to be on the bottom, and I'm entering moles of NO2, so that's going to be on top. So we have to look at the coefficients here. So for moles of oxygen, that's number 2. So it's going to go down there. For moles of NO2, that's also number 2, so it'll go up there. So it's just 2 over 2 here. Right, so this is doing it like a normal stoichiometry problem. However, whenever you go from liters to liters, right, if you're going from liters of gas to liters of another gas, whenever you do this little step in stoichiometry, you can do it quicker, right? Because if you notice something, I have 22.4 here, and I have 22.4 up there. They're just going to cancel. Right, the first and last fractions here are just going to cancel completely. So the only thing that really matters is the mole fraction. So it was 42.1 liters, I believe, was what we were given. 42.1 liters, yeah. So the trick here because these first and last fractions are just going to cancel, because it's 22.4 on the bottom, 22.4 on the top, they're just going to cancel anyways. Because that's going to happen, you can just use the coefficients from the balanced equation, and instead of calling it a mole ratio, you just call it a volume ratio instead. So in this case, it's the same on the top and bottom. It's 2 over 2. It's not always going to be like that. It just so happens to be like that this time, right? So I'm just going to use that one fraction, just 2 over 2. So in this case, this question's kind of silly in a way because we get the exact same answer as our given, 42.1 liters. It's not always going to be the same on the top and bottom here. If it asked for liters of nitrogen, for example, if it asked for liters of nitrogen instead of NO2, then I would have 1 on the top, right? So in that case, it would be a different answer. I'd have 1 on top instead of 2. So in this case, it just happened to be the same number on the top and bottom. But the whole point here is if you're going from liters of one gas to liters of another gas, if you're going from liters to liters, you don't need to do the whole entire stoichiometry thing like this. You just need this one fraction. And this one fraction we usually call the mole ratio. But since we're going from liters to liters, you can just call it the liter ratio or the volume ratio. And the numbers here are just the coefficients, right? So you just need this one fraction. So that's what we have here. And the coefficient of liters of oxygen is down here, which is 2. The coefficient for liters of NO2 was up here, which is also 2. In this case, they're the same number. It's not always going to be like that. It was just like that in this case. So yeah, just to kind of make a long story short, if you go from liters to liters, just multiply your given by the volume ratio using coefficients. Yeah, so if you're just going from liters to liters, just multiply it by that one fraction. it's the same as the mole ratio when we're doing stoichiometry in that last unit. So you're using coefficients. So you have to balance the equation first and put the coefficients there. That's where these 2's came from. But we just call it volume ratio instead because we're trying to get liters. Yeah, in this case, it's kind of a silly question. We ended up with the exact same number. It's not always going to be like that. That was just this problem. It's not always going to be like that, though. Yeah, hopefully that sort of helped. But yeah, let me know if you have any other questions at all. Oh, nice, Mohammed. I'm glad you're able to keep up with it. But yeah, let me know if you guys have any other questions about anything at all. And yeah, even with the tests and quizzes, because of just how crazy things are with this whole COVID-19 and trying to learn from home, you can retake them. So if you don't like your grade that you got originally on a quiz or a test, you can take it again multiple times if you want. You can just keep retaking it. Oh yeah, they're very different things. So enthalpy, it's kind of a complicated definition. I'll try to write it out. So really, enthalpy is the heat content of a system. So this could be a liquid, a simple solid object. It could be a gas, any sort of object, and you're calling this like a system. It could be multiple objects interacting with each other, but you call this a system. So system can be kind of arbitrary. It's just whatever you're studying and everything outside of the system's surroundings. But when it comes to a system, enthalpy is the internal energy of that system plus the product of the pressure and volume. Now, we're not really going to worry about the pressure and volume so much in this unit. So we're going to typically just think of them as constant. So you can think of enthalpy as just the internal energy of the system. So it has units joules, just like energy. So it has units joules. Right? So enthalpy is always given this delta symbol in front of it. H is enthalpy, by the way. So H, it's not heat, it's enthalpy. I'm not sure why it's called H. It might have came from the idea of heat, but it's a different idea than heat because heat is energy going from one object to another, right? From a hotter object to a cooler object. That's what heat is, just the transfer of energy between. So heat's fluid. Heat is something that moves, basically. Enthalpy is the internal energy. So it's always given with this delta symbol because we're looking at the internal energy of a system that's changing because it's not typically always staying the same. So if it's positive, it's endothermic. If it's negative, it's exothermic, right? Because if it's positive, it's absorbing internal energy. The change in internal energy is getting bigger. So it's absorbing energy from outside in the form of heat. And so it has a higher internal energy. If it's negative, it's releasing its internal energy as the form of heat to the surroundings. So it's exothermic, right? So when it comes to enthalpy, it's just that internal energy of the system itself. Based on just the heat content of the system, the motion of the particles within the system, the energy within their bonds. You can really just think of it as like the internal energy though. And so when we look at things like Later on, I don't think these notes are up yet. They'll be up early next week. We're going to look at enthalpy changes for chemical reaction equations. So I'm just going to make something up right now. It's not an actual equation. I just put R and P for reactants to products. So something like this, if I have a reaction, so the reactants are on the left, the products are on the right. And next week, we'll see that we'll have enthalpy values for chemical reactions. Now, the process, in order to go from reactants to products, in order to go from a reactant to a product, conservation of mass says the atoms have to be the same on both sides. That's why we balance these equations. So the reactants have to break apart their chemical bonds, right? Their chemical bonds have to break apart in order to reform their bonds as products, right? So basically, when it comes to bonds breaking, here, let me just write this down real quick. Bonds breaking requires them to absorb heat from their surroundings. Oh, I wrote this wrong. So bonds breaking is actually endothermic, right? So to go from reactants to products, the chemicals on the reactant side need to break apart their bonds. In order for them to break apart their bonds, now, if you think about like this, when we draw these Lewis structures like of O2 or CO2 or CH4 or whatever the substance is, the Lewis structures follow the octet rule. They're trying to be stable. They want to be like that. So they don't want to necessarily get ripped apart. So in order for them to break apart their bonds, they have to be endothermic. Right? Hopefully that looks like endo. It should say endo. So their bonds breaking need to absorb heat from the surroundings. So it's endothermic to break bonds. And then to form new bonds as products over here, to come together and form bonds of a product, that's exothermic. Right? So let me just write that a little bit better. That's exo, that's endo. Right? So breaking bonds in the reactants is endothermic. Forming bonds in the products is exothermic. So P is endothermic, right? If delta H is positive, it's endothermic. It's absorbing heat and making the internal energy increase, being released as products, right? It didn't just disappear or anything. It's still in there. It's just in the chemical bonds. So more energy was being absorbed in the reactants than was being released in the products forming. If it was negative, let's say it's the same number, but it's negative, this means it's exothermic, right? If the delta H, if the enthalpy is negative, it's exothermic. So more energy was being released to form these products than was being absorbed to break apart the reactant bonds. So basically, to cut a long story short, enthalpy is just the internal energy within a substance. It's measured in joules like heat, like energy, but energy is kind of like just the most vague umbrella term for the whole entire thing. Heat is the transfer of energy in between two different bodies from hot to cold. Enthalpy is looking at that energy within the actual systems, the actual substances themselves within their chemical bonds and so on and so forth. So that's what enthalpy is. Entropy is something very different. Entropy deals with the tendency for that to happen and how spontaneous it is. So entropy is really a measure of multiplicity. Let me see if I can define that well. So yeah. One second. So entropy is a measure, you usually see it in textbooks saying it's a measure of disorder, and that's absolutely true. Sometimes that description can get kind of difficult because we kind of subjectively think of it as something going wrong, but disorder naturally happens. That's just the way it is. It's really just multiplicity, like most combinations. So entropy actually has units, joules per Kelvin. Joules per Kelvin, so it's basically energy per temperature, enthalpy per temperature. And it has this letter S, and this is the most basic equation for entropy. I'll show you guys this on the notes, but we're never going to use it. You're never going to have to worry about it. Basically, entropy is a measurement of disorder. So the best example I can kind of give is if I have 2 quarters and I want to figure out how many combinations I can have of, it's probably not the best case. Let's just say 3 quarters. All right, so if I have 3 quarters and I want to see how many ways can I get 2 heads and 1 tail. So I have 3 quarters, I want to flip them and see how can I possibly get 2 heads and 1 tail. So you can either get 2 heads first and a tail, you can get a head, tail, then a head, or you can get a tail and 2 heads. So this combination of 2 heads, or this possibility of 2 heads and 1 tail, we call a macro state. And all the different variations that we can get that, we call microstates. All right, so it's kind of a weird example. This will be on Canvas next week in the notes. But if I have 3 quarters and I want to get 2 heads and 1 tail, I want to flip them and see how I can get 2 heads and 1 tail. That possibility of 2 heads and 1 tail, that's the macro state I'm trying to reach. The possible ways you can attain that, and there's only 3 here, those are the microstates. That would be 3 microstates. Microstates is that little omega sign. That little omega in this natural logarithm, that's microstates, the number of possible combinations you can get. And so it's a natural logarithm, so it's based on the letter E, or the number E, Euler's constant. So basically, entropy is a measurement of disorder and possible combinations, because we're learning about thermochemistry right now and thermodynamics, and really thermodynamics is all about particles in motion, right? Because we know things that are at a higher temperature have particles moving at higher velocities. There's more energy within the system. Objects that are at a lower temperature, their particles are moving much slower. So when you really think about it, thermodynamics is just all about statistics. At the high, like, university level, you'll take an introductory thermodynamics class if you're a physics major, and then if you go above that and want to like specialize in it, it's a class called statistical mechanics, because thermodynamics is just all about the possibilities that these particles are going to be in this state. So for example, if I have a collection of like, if I have 3 particles at, I'm just going to say like 12 degrees Celsius, something kind of small like that. If I have 3 particles bouncing around, this is very unrealistic, by the way. I'm just thinking of something just to kind of make it more understandable. If I have 3 particles and they're at 12 degrees Celsius, 12 degrees Celsius and 3 particles, that's the macro state. That's like 2 heads and 1 tail for 3 quarters. That's the macro state. But there's like so many millions or thousands of different ways you can attain that from the 3 particles. And those are how many microstates you're going to have. That's the omega, how many microstates you can possibly have to get that temperature from 3 particles. So you could have them like that, maybe you could have them in slightly different locations, like that one's over there, this one's over here, and that one's over there. So there's so many different possible combinations. You can possibly get that temperature of that many particles. So entropy is just a measure of disorder. So if you have more particles, like 3 million particles, for example, there's going to be even more microstates, even more possibilities you can get at that temperature of like 3 million particles, right? So entropy is a measure of disorder, and at the end of the day, it's important for thermochemistry because it explains why heat goes from hot to cold, why heat transfer always goes from hot to cold, right? Because if you think about it like this, I'm just gonna try to draw it out real quick. Heat always flows from hot objects to cold objects, and that's all about entropy. That's about this this multiplicity and this idea of disorder increasing. Because if something if something has more internal energy, more enthalpy, it's going to more likely be exothermic. It's going to more likely radiate its heat, right? Because if it's at a higher temperature, the particles are moving faster, they're spreading out more, they have a higher velocity. That's why these arrows are bigger, and there's like some motion lines around the particles. And the cold objects aren't moving that much in comparison. They're moving a lot slower. So they're more likely to get bumped into by these guys. These guys are going to bump into them and then cause them to move a little bit faster. And as they bump into them and cause them to move a little bit faster, these guys are going to slow down a little bit until they're both the same temperature. So entropy is really just a measure of disorder, but it explains why heat always goes from hot objects to colder objects, because it's all based on the possible combinations you can have of particles at certain temperatures. So if particles are at really, really high temperatures, like 100 degrees Celsius or 250 degrees Celsius, there's way more possible ways that they can be moving around each other because they're moving faster, right? So since they're moving faster, they're going to be spreading out more, bumping into each other more. There's way more possible combinations. There's like probably millions of microstates there. But if something's at a lower temperature, they're not moving as fast. So there's a good amount of microstates, but in comparison to a higher temperature, they're not going to be moving as fast. There's less combinations for them to be at that temperature. But there's other examples too. Basically, it's part of the second law of thermodynamics, which we're not going to go too much into, but it just says that for the universe, entropy always increases, and for any closed system, entropy increases because, for example, if you have like an ice cube sitting here on the table, no matter what, the ice cube is going to melt, right? Because its particles are moving much slower. The air molecules outside of it are moving way faster. They're at a higher temperature, right? They're warmer compared to the cool, cold ice cube. So they're going to bump into the ice cube, cause them to vibrate a little bit more, keep bumping into the ice cube, causing the ice cube to kind of move a little bit more until eventually they're moving so much that now they're a liquid, right? They've melted. And the air around the ice cube might be a little bit cooler because it slowed down as it was bumping into the ice cube. So it explains that whole process of heat going from hot objects to cold objects. But it really just governs everything. So things like gases have a lot of entropy. Liquids, it's more medium. Solids have very low entropy because the particles in a solid don't translationally travel. They don't go from point A to point B. They stay in their own little regions. They just vibrate and just shake. Whereas gases maximize their volume, right? If you have a poisonous vial, like if this iced tea was a poisonous gas and I opened it up, if you're on the other side of the room, you're probably still going to be in danger of inhaling it because gases like to maximize their volume, right? Yeah, it's very much related to probability and statistics because it's based on microstates, which is just the possible combinations you can have for this system to be at a certain temperature value or a certain energy value. It depends on what you're really looking at, what you're trying to measure, basically. But yeah, it's based on probability. So this equation, I'll mention it in the notes next week. S is entropy. We're never going to use it. You're never going to have to worry about it. But K is something called Boltzmann's constant, and it's measured in joules per Kelvin, so that's the units of energy. And this is just the natural logarithm for the number of microstates. So if the microstates are really big, like 3,000 compared to 3, it's going to be more entropy. It's going to be a higher entropy. So it's very different than enthalpy, but it also relates to enthalpy. It has a relationship to it because if something has higher enthalpy compared to something that has lower enthalpy, it's more likely to radiate its heat exothermically to the colder object. Other examples could be like, for example, if you have, like here, let me find it. I saw it the other earlier. One second. Here, hopefully this comes out in the chat, because this is another good example. It's less chemistry based, I guess you could say, but I don't know. I think it gets the point across pretty well. Oh, I guess that's not working. Let me do it this way. Hopefully this works. That picture there is a good example. So if you have like a jar of jelly beans that are pink and white, and you shake it a bunch of times, it's always going to be mixed up. It's always going to be more disorderly. It's just a higher probability that they're going to be all mixed up a bit more. Technically, the probability isn't 0 that they're all going to be layered like pink and white, but the probability is like 0.000000. It's like pretty much impossible. Not exactly impossible, but it's not really going to happen. Right? So that's basically a good pictorial example of entropy comparisons. And so if I have something that I want to stay, like if I have water, which should be a liquid at room temperature, and I want it to stay frozen, it's not going to stay frozen out here. So the only way it can do that, the only way you can get more order and less disorder is if you manipulate it a bit more. So put it in the freezer. If you put it in the freezer, you're adding energy to the system in the form of electrical energy. So you're allowing it to stay frozen because of the electrical energy that's powering the freezer to work and keep it at that low temperature for so long. So entropy just says spontaneous things always tend towards disorder. So having a jar of jelly beans that are pink and white, spontaneously, if it gets bumped around or moved around, someone bumps into it, it's going to get mixed up. It's not going to spontaneously be all ordered like pink and white. It's not impossible per se, but it's like 0.100 zeros or so. It's really unlikely. And we kind of see later on that they all kind of get tied in together. Yeah, enthalpy is proportional to the temperature times the change in entropy. So enthalpy, which is the H, the internal energy of a system. So that's the energy content of a system due to like the energy within its bonds, the energy of the motion of the particles. It's proportional to the temperature times the change in entropy of that system. So if you have something that's exothermic, for example, if it's exothermic and releasing internal energy, then that means actually, let me double check that. Yeah, that means that the change in entropy is also going to be negative as well. The changes in entropy is going to be negative. So more spontaneous things are like that. So spontaneous things happening. This is all stuff we're going to look at next week, by the way, so we're kind of getting a head start. Spontaneous things are going to be negative enthalpy, so exothermic, it's releasing energy, as well as negative changes in delta S. All right, so let me double check real quick. Or I shouldn't say negative, actually. I'm sorry, it's positive. My bad. It's positive delta S. I got mixed up with something else I was thinking about. Positive delta S. Yeah, positive delta S. Yeah, so spontaneous things happening would be a negative enthalpy change, so it's releasing internal energy, and a positive entropy change, so it's more disordered. So, basically, good examples are kind of like those gumball examples and things like that. So, let me see. Right, so here's another example with entropy. Oh, come on. Where is it? I guess I'll just have to explain it. So if you have an egg, for example, an egg just sitting on the table, spontaneously, if something happens, like there's an earthquake and it rolls off, or someone bumps into it or something like that, there's so many different ways it can crack. It can crack in half, it can crack down the middle, it can crack on the corners, and there's even more ways it can be smashed. Right? If something falls on it, it can be smashed in this many different shapes of cracks, this many different segments of the eggshell. There's so many different ways that it could possibly be smashed up or cracked. But there's only one way it can be a completely formed egg. So if you have like a cracked egg on the ground, a smashed up egg, and it's getting bumped into by other things, it's highly unlikely that it's going to have all the egg go back into a specific spot and all the shell form exactly and seal. It's highly unlikely it's going to happen. There's only one way the egg can be complete. There's so many different ways the egg can be smashed. And so it's the same when it comes to systems of particles, things like gases and liquids. When they're at higher temperatures, there's so many different ways those particles can be oriented at higher temperatures. They can be moving at different speeds over in this corner and that corner. This corner can be a little bit faster, and this one's maybe a little bit faster, and this one's a little bit cooler. But there's so many different ways for the particles to orient themselves and move around themselves at the higher temperatures. But at really, really super cold temperatures, like when it's a solid, as a solid, there's a good few different ways it can be at that temperature, but way less compared to like a gas, something at a higher temperature. So gases, things that are at higher temperatures, they have more possible ways of being at that of many microstates. They can there's more possible ways they can be in that state, basically. So it gets kind of tricky. But yeah, I go into a lot more detail with it on the notes next week, and there's like a few videos that are kind of helpful too that I put on there. That's not a good picture. Yeah, let me know if you have any other questions or anything. Entropy and enthalpy are very different. They relate to each other, but they're very different things. Hmm. I'll probably stay on for a little bit longer, but I might get going if no one has any other questions for now. All right, see you later, Ryan. Have a good one. So let me know if you have any questions or anything. I might go in a couple minutes, though. And I'll probably take off, but if anyone's there, just let me know if you have any questions later on. But hope you have a nice rest of your day and take it easy.